Hi, my name is Jonathan Fuller, and today Mingchuan Yao and I will be presenting our paper, Enhance Web Application Security Through Proactive Dead Drop Resolver Remediation. We'd like to thank our other co-authors and institutions, the United States Military Academy and the Georgia Institute of Technology, for their support. Dead drop resolvers are public web applications used by command and control orchestrators to hide their command and control addresses in plain sight. Upon infection, the malware connects to the DDRs to retrieve the address. The malware then decodes the CNC address using one or more decoding schemes to reveal the CNC server domain or IP before using that to connect to the CNC server. There are several advantages to this approach, like the numerous web apps that are freely available to use, providing anonymity and elasticity. DDRs also allow for unlimited CNC server endpoints that are truly unpredictable and easily migrated. Furthermore, the network traffic generated by web app access seems benign and it's not easily distinguishable. Lastly, CNC orchestrators generally use multi-encoding to masquerade the true intent and prompt intensive analysis by investigators to decipher posted messages. These traits make dead drops nearly invisible, but today we'll show you how you can finally turn visibility back on. So how do we stop DDR malware? Well, this question led us to three key insights. And the first is that DDR malware samples must decode CNC addresses for use. Thus, the malware contains the decoding logic. Now, if investigators understand how the malware's demanipulation logic works, they can decode web app content to proactively find dead drops. But how can we find this demanipulation logic? So imagine an investigator observing a network connection to a web application, followed by another connection to a CNC server. Well, determining whether the malware contains DDR logic in this scenario can be extremely challenging because the raw network content from two connections often look completely unrelated. In reality, the way DDR operates enforces a data flow from the initially fetched web content to the decoded CNC address. This observation leads to our second key insight. Investigators can localize the DDR routines by tracing this information flow through the malware's execution. Now, once we isolate the demanipulation logic, how do we know what specific algorithms like XOR or character rotate are used? Well, demanipulation routines can, in fact, be mathematically represented as a series of arithmetic and logical operations, which can be collectively expressed as symbolic expressions. Well, what if we could extract these symbolic expressions? This led us to our third key insight, which is symbolic expressions can be matched to known algorithms to extract demanipulation recipes. That is, these expressions give investigators an implementation agnostic recipe. So by comparing symbolic expressions extracted from the malware's DDR logic with expressions derived from known algorithms, the investigators can recover the exact demanipulation steps that the malware used. Now, armed with our key insights, we can move to proactively discover previously unknown dead drops or turn the visibility back on. So how do we leverage those insights in VADER? Well, let's look at our framework at a macro level to understand its components and results. So firstly, VADER takes malware as input. In this case, we use the muddrop malware as a running example. Analysis begins with DDR logic localization, where VADER tracks the connection and data retrieval from a web app. If this data is then used to establish a subsequent outbound connection to the CNC server, VADER has confirmed DDR capabilities and the logic is isolated. So in this instance, VADER identified a connection to a WordPress and the retrieval of a dead drop content. Next, VADER conducts demanipulation boundary isolation to identify the regions where demanipulation occurs in the binary. So given these identified regions, the symbolic expressions derived during malware analysis are extracted for demanipulation recipe identification. In this case, VADER identified base 16 and character rotation used to decode the dead drop content. The concolic analysis-driven approach proved to be tractable and effective, allowing us to identify DDR malware at scale. Now, armed with the demanipulation recipe, we were enabled to perform DDR recipe scanning of captured network traffic and web app data to identify dead drops, And then this proactive approach led to the discovery of 3 additional previously unknown dead drops, which multiplied our efforts. Now, in collaboration with Netscope, a leading secure access service edge provider, delivering cloud security and network solutions to over 30% of the top 100 enterprises, we deployed VADER on a dataset of 100,000 Windows malware samples, which were collected between 2012 and 2022. Of the 100,000 samples, VADER identified 8,906 DDR malware samples and 7 unique demanipulation recipes. VADER found Pastebin to be the most abused web app, accounted for roughly 68% of all DDR malware found. So this isn't too surprising because Pastebin has long been used for malicious purposes. However, it has generally been used to host stolen content or malware to be dropped on victim systems. This work is among the first to expose its pervasiveness as a hosting platform for hidden CNC addresses. Surprisingly, VADER also found that 5 out of 13 web apps are blockchain explorers, accounting for roughly 25% of all DDR malware identified. We noticed that most DDR malware use a blockchain explorer, or most DDR malware using a blockchain explorer use more than one as backups, but each of the malware only use one wallet ID. We identified a total of 14 wallet IDs. So CNC orchestrators buy Bitcoin, which updates the transaction ledger, and then the malware retrieves the most recent transactions and converts them to an IP address, which it uses to contact the CNC server. Interestingly, VADER also identified a few Twitter DDR malware that exhibits a hybrid approach, using a domain generation algorithm to generate pseudo-random Twitter accounts. In these cases, investigators can leverage existing domain generation algorithm counteracting techniques to thwart these types of hybrid DGA and DDR malware. We also notice a few cases of popular web apps used. We assume that since several works have studied popular web app abuse, though none consider DDR, malware authors are likely using less popular web apps to reduce suspicion.
Given the capability of the generated recipes, we're looking forward to how to apply the recipe in a large scale so that we can even proactively find more DDRs beyond our malware data sets. So that motivates us to apply VADER on the NetResec PCAP data sets. As we can see here in this table, beyond the original web apps VADER identified, by applying the recipes generated from VADER on this PCAP dataset, VADER found 72 additional dab drops hosted on 11 web apps. And not surprisingly, base64 is the most popular choice, which amount 40% for the attackers. And given all of those findings, VADER actually identified those 67 CNC server addresses. And 60% of the data drops remain available during the time of study. However, given the capability of finding those CNC server addresses, we can actually prove to the service providers these are actually data drops, you can remove them. And in fact, that's what we did during this study. VADER helped remove 88% of the active data drops during our study.
So, stepping back, what did we actually achieve with VADER? Well, VADER moves us beyond reaction. It proactively uncovers and neutralizes the dead drops that DDR malware relies on before the CNC channels ever go live. Now, we tested it at scale, 100,000 malware samples across 110 families and 7 major web apps, and found 273 active dead drops hidden in plain sight. So by learning the malware's own decoding logic, its recipes, we improved discovery network traffic by 57%, which is a major jump in visibility. Working with web app providers, we removed 94.4% of identified dead drops, cutting off control for over 6,600 active malware instances. And the best part, this isn't a one-off instance. The same approach can scale to any platform. It gives web app providers a reusable blueprint for proactive CNC defenses. Thank you for listening to our talk. There's much more in the paper, including how we built our 100,000 malware sample dataset in partnership with Netscope, and our outreach and data sharing collaboration with web app service providers, and how web app vendors and IDSs can use VADER generated recipes. Many thanks for our partners and especially Netscope for aiding us along this research journey. Thank you.